In the heart of Rome stands one of the Eternal City's most famous and well-preserved ancient monuments, the Pantheon. Constructed during the reign of Emperor Hadrian in the 2nd century CE, the building has been in near continuous use for 2 millennia, first as a temple dedicated to the Olympian gods and then as a Catholic basilica. Home to exquisitely preserved Roman architecture and the tombs of such luminaries as the artist Raphael and King Vittorio Emanuele II, the Pantheon has inspired the design of buildings around the world and remains one of Rome's most popular tourist attractions, visited by some 6 million people every year. But perhaps its most celebrated feature is its 43-meter coffered dome, crowned by a 9-meter circular oculus or opening that floods the rotunda below with light. Incredibly, this impressive structure is not built, as one might expect, of marble or brick, but rather of concrete. Even more impressively, it contains not one piece of rebar or other structural reinforcement, making it the largest unreinforced concrete dome in the world. Indeed, the Romans were masters of concrete construction, building all sorts of massive structures from harbours and aqueducts to the famous Colosseum from this versatile material. Hello there, do you love coffee like me? Are you I don't know if they want me to use the word addictive in the ad read, but oh my god, I love coffee. I can't live without coffee. And if you're like me, well, you're in luck. Because today I want to give a shout out to our fantastic sponsor, Trade Coffee. It's like Christmas morning every time it arrives in your mailbox. Look, if you're tired of mediocre coffee, and who isn't? No one likes mediocre coffee. Well, Trade has got your back. They'll connect you with the best roasters in America. Over 450 coffee makers. Yes, you heard that right. Dark roasts, espresso blends, even some super rare finds. You can try everything from smoky dark roasts to vibrant fruity blends. For me, it's all about that dark roast. I like that. And let me tell you, it's a bit of a flavor roller coaster, but the magic doesn't stop there. Freshness is key. Every bean roasted is to order and shipped directly to your door within 48 hours. It's like having some sort of personal coffee wizard at your beck and call. Worried about where to start? Well, don't be. Trade's matching algorithm finds coffees tailored to your taste buds. It's like having a personal barista in your pocket. Plus, their subscription plans are super flexible. You can tweak them anytime, and shipping is free. It is coffee heaven. So here's the deal, fellow coffee lovers. You can join this coffee revolution. Just click the link in the description below or go to drinktrade.com/brainfood. And guess what? You'll score a free bag of coffee with any subscription. Don't miss out on this chance to upgrade your coffee game. Do it today. There's a link below. Thank you to Trade for sponsoring. Now into today's video. This fact may shock and confuse those of us living in the modern world, where one bad winter is often enough to turn concrete roads and bridges into something resembling the surface of the moon. So, what allowed Roman concrete to last millennia, while modern concrete crumbles after just a few years? Well, Roman concrete is known to have reached widespread use around 150 BC, though most archaeologists believe it was first developed nearly a century earlier. Like its modern counterpart, Roman concrete has 2 basic components: cement, a powder that sets hard when mixed with water, and aggregate, a mixture of gravel and other small hard particles that add strength to the mixture. Modern cement, known as ordinary Portland cement or OPC, is made by heating limestone as well as various other ingredients including clay, iron ore, sand, gypsum and coal ash in a kiln to produce a lumpy mixture called clinker. The clinker is then ground down to produce cement powder. The composition of Roman concrete was broadly similar, consisting largely of calcium oxide or quicklime made by heating limestone in a kiln. This was then mixed with pulvis or pozzolana, a fine glassy volcanic ash found mainly around the Bay of Naples. Pozzolana was considered the secret source of Roman concrete, so much so that hundreds of thousands of tons were shipped across the Roman Empire as far as Alexandria, Egypt, for use in construction projects. There were, however, some significant differences between Roman and modern concrete. For example, while modern concrete uses aggregate mainly composed of sand and pea-sized gravel, Roman aggregate, or caementa, consisted of larger, fist-sized chunks of volcanic stone called tephra and pieces of brick and other recycled building materials. Like modern concrete, Roman concrete hardened not by drying, but via the hydration and crystallization of the calcium aluminium silicate compounds, also known as stratolingite, formed from the reaction of quicklime and pozzolana and could thus set in the absence of oxygen, even underwater. This allowed the Romans to build concrete harbour piers, breakwaters, and other underwater structures without the need to build dry cofferdams. The earliest example of such hydraulic cement being used is in the construction of the harbour at Baiae near Naples in the late 2nd century BCE, while its larger scale application was the harbour of Caesarea Maritima in modern-day Israel, whose concrete piers are still intact to this very day, despite being exposed to the Mediterranean Sea for 2 millennia. This remarkable longevity baffled architects and material scientists for decades, for while the long-term survival of surface structures like aqueducts is impressive enough, immersion in seawater is ordinarily lethal to concrete, causing it to crumble within decades. Yet not only have the piers at Caesarea Maritima survived, they've actually gotten stronger over time. Even more bafflingly, in terms of sheer compressive strength, Roman concrete is actually 10 times weaker than modern OPC-based concrete, yet somehow many times more resilient. So, what's going on here? To uncover the secrets of Roman concrete's remarkable resilience, in 2013, a team of researchers led by Paolo Montiero, a professor of civil and environmental engineering at UC Berkeley, analyzed samples of concrete from the piers at Caesarea Maritima. To their surprise, they discovered crystals of a rare calcium silicate hydrate material called tobermorite. These crystals, they deduced, were formed via the reaction of the material philipsite in the pozzolana ash with seawater that had percolated into the concrete. Not only is tobermorite harder than any of the concrete's original constituents, but its formation traps molecules like chlorides and sulfates that ordinarily damage concrete, meaning, amazingly, that immersion in seawater actually makes Roman concrete grow stronger and more durable with time. As well as potentially improving the performance of modern concrete, this discovery may have wider applications in industry, as aluminous torite normally requires high temperatures and large amounts of energy to synthesize. Another key to Roman concrete's durability lies in one of its most historically baffling features, the presence of brittle white inclusions called lime clasts throughout its structure. For decades, archaeologists attributed these inclusions to poor quality raw materials or sloppy mixing practices. However, some experts like Admir Massic, a professor of civil environmental engineering at MIT, were skeptical of this explanation. He states, "The idea that the presence of these lime clasts was simply attributed to low quality control always bothered me. If the Romans put so much effort into making an outstanding construction material following all of the detailed recipes that have been optimized over the course of many centuries, why would they put so little effort into ensuring the production of a well-mixed final product? There has to be more to this story." Indeed, in his 10 books on architecture, written in 25 BCE, the great Roman architect Vitruvius laid out extremely precise recipes for concrete, while Emperor Augustus, who reigned from 27 BCE to 14 CE, spearheaded major construction and restoration projects in Rome that resulted in the widespread systemization and standardization of concrete manufacture. In 2022, the team, led by Massic, conducted spectroscopic analyses of concrete samples from the mausoleum of Roman noblewoman Caecilia Matea, built between 20 and 10 BCE. These analyses revealed that the lime clasts are composed of various types of calcium carbonate and oxide, which are much more brittle than the surrounding cement matrix. Whenever the concrete shifts, either due to the ground settling or the earthquakes that commonly plague the region, this brittleness causes cracks to form preferentially within the clasts. However, rain or groundwater percolating through the concrete reacts with the clasts, promoting the growth of calcium carbonate crystals that eventually fill and reinforce the cracks. This reaction effectively makes the concrete self-healing, filling small cracks before they could grow into larger and more dangerous fractures. Now, to test this theory, Massic cast and cracked 2 samples of modern and Roman concrete and ran a stream of water through them. As predicted, within 2 weeks, the cracks in the Roman concrete had sealed themselves, preventing the water from flowing through. Massic's analysis also revealed that the lime clasts could only have formed at high temperatures, indicating that the Romans mixed their concrete very differently than modern builders. Today, quicklime is mixed with water, producing calcium hydroxide or slaked lime before being added to the concrete mixture. The Romans, however, added quicklime directly to the mixture, a technique known as hot mixing. Not only does hot mixing produce the high temperatures needed to form the self-healing lime clasts, but it also reduces overall curing time, allowing for faster construction. But clever chemistry isn't the whole story here, and the final key to the remarkable longevity of Roman concrete lies in the specific manner that it was cast. According to Vitruvius, unlike modern concrete, which is mixed wet and poured, Roman concrete was mixed dry with as little water as possible, with the resulting putty-like mixture being troweled into place. Large pieces of aggregate, like volcanic tephra and brick or building stone fragments, were then laid atop the concrete before another layer of concrete was troweled on top. The whole layer was then tamped down using special tools. By tightly compacting the mixture, and reducing its water content. Roman builders minimized the formation of voids within the structure, the main source of weakness in concrete, and promoted the formation of tough stratlingite crystals. Interestingly, the advantages of this construction method were confirmed by a much more recent construction project, and that's the building of the Upper Stillwater Dam in eastern Utah in 1987. The concrete used in the dam's construction was composed of 40% OPC and 60% coal ash, closely replicating the lime pozzolana chemistry of Roman concrete. This mixture was mixed with minimal water to form no-slump concrete, which was spread in layers and compacted into place using giant vibrating rollers. Later analysis of the dam structure has revealed many of the same self-healing properties exhibited by Roman concrete. These various chemical mixing and layup tricks combined to create what Philip Brun, a research scientist at DuPont Chemical, calls, quote, an extraordinarily rich material in terms of scientific possibility, the most durable building material in human history, and I say that as an engineer not prone to hyperbole, end quote. Indeed, scientists and engineers around the world are actively studying the secrets of this extraordinary ancient building material in order to improve the efficiency and durability of modern concrete, an urgent task given our current climate crisis. While concrete is an extraordinarily versatile material with 19 billion tons being used every year worldwide, it has an equally outsized impact on the environment, being responsible for up to 8% of global CO2 emissions. Most of these emissions come from the production of clinker, which requires temperatures of 1,450 degrees Celsius and consumes large amounts of fossil fuels. The use of motor vehicles to transport, pour, and repair concrete also contributes to this carbon footprint, a problem made all the worse by the low durability of modern concrete. Roman concrete, by contrast, is made from ingredients fired at much lower temperatures, thus requiring less fuel, and lasts much longer, greatly reducing the frequency with which it must be replaced. And while Roman concrete's secret ingredient, pozzolana ash, is relatively rare, studies have shown it can be replaced with readily available coal ash with little reduction in performance. Indeed, Roman-style concrete made with fly ash could cost up to 60% less to produce than regular OPC-based concrete, providing a powerful incentive for builders to switch over. Thus, with any luck, this wonder material from 2 millennia ago may very well help ensure that our current civilization will last another 2 millennia. But then again, well, what have the Romans ever done for us?